In this segment, we'll introduce relational algebra, RA, starting with projection and selection operations on relations. And we'll look briefly at how relational algebraic expressions might relate to optimizing the execution of select statements. So, first of all, RA deals with operations on relations, as discussed in the prior segment. So we'll start with the RA means of describing a relation's name and its constituent attributes, though not its actual content. And this is done via something called a schema in the RA context. The notation RA uses for schemas is quite similar to the create table statement from SQL. Relation schema is the relation name, like customer here, and then a parenthesized, comma-separated list of its attributes, each providing an attribute name and type separated by a colon. So not too different from the SQL create table statement, but perhaps a little lighter on the details of the types. Question 1. Show the schema for the relation that corresponds to our bakery 1 table line item. Just write out that format for line item. And you should have come up with something that looks like this. And that's about it. Pretty straightforward question. So now that we've developed a theoretical view of tables as relations, let's extend it to a theoretical description of SQL-type operations. Here the motive is not just to generalize the concepts, but also to provide a notation that's less cumbersome than SQL syntax and can be used later when simplifying and reorganizing sophisticated SQL queries, as is done by DBMSs when they optimize a SQL query for execution. So a select statement, for instance, lets you pick the columns retrieved from a table. In effect, this produces a smaller table comprising only those columns. This seems a simple enough feature, but it gets its own special term and concept under RA. Reducing the tuples in a relation by one or more attributes is called projection. Mathematically, projection reduces the horizontal dimension, if you like, of the relation to produce a new relation of fewer attributes, as shown in the diagram here. And by the way, we'll discuss the pi symbol in a bit. A brief aside here, why the term projection? Well, consider this example. Say we have a relation of 3 attributes, 3 columns, and call them x and y and z. And let's let each one be an integer between 0 and 100. In that case, tuples of the relation, rows of the relation, could be viewed as x, y, z points in a cube of dimensions from 0 to 100. The relation can be viewed as a set of 3D points, if you like. Eliminating one of the attributes, say z, reduces the tuples to 2D points. In the case we're giving here an xy plane. Visualize that. Each 3D point is projected or flattened onto the xy plane by keeping its x and y attributes and dropping its z attribute. And the resultant relation is, again, a set of 2D points. Reducing an n-dimensional set of values to a lower number of dimensions, as by eliminating one or more of the values, is termed projection in many mathematical contexts. You'll hit the same idea in graphics, robotics, linear algebra, and so forth. Now, no good abstraction is complete without a mathematical notation, preferably using Greek letters. So let's represent a projection that picks attributes A, B, and C from a relation R. Thus, pi subscript ABC, operating on relation R here. So, for instance, the relation obtained by selecting first name and last name columns from the relation customer could be written as pi of first name, comma last name, operating on customer, as shown in the transcript here. The pi, predictably, is for projection. Okay, so that covers select. What about where clauses? SQL's where clause, selecting certain rows of the table, is abstractly termed a selection on the relation. Like a projection, it can be viewed as producing a new relation from the old one, in this case not by cutting attributes but by taking a subset of the tuples. In the Greek lowercase sigma represents selection, with the where clause given as a subscript. So, for instance, if I wanted to select for price greater than 10.0, I'd write it here in the subscript next to the sigma symbol. And that signifies selecting only those rows or tuples from product whose price is greater than or equal to 10.0. Using the term selection, by the way, for the where clause operation and projection for the SQL select operation is a bit confusing. Remember that in relational algebra terms, a select operation is not what the SQL select clause does. It's what the where clause does. The SQL designers should probably have used some different keyword than select for what is actually the projection operation. Maybe they could have made it choose from instead. And of course, you can compound these operations into larger algebraic expressions. For instance, the relation that gives just the kind and flavor of all products costing $10 or more is translated from SQL, select kind flavor from product or price greater than or equal to 10.0, to relational algebra, project kind and flavor from select price is greater than 10.0 on product. As is typical for nested function mathematical notation, you should read that expression from the inside outward, of course, starting with product and performing the select to get just the tuples with the desired price, and then projecting only the desired attributes from those, arriving at a relation with only a few rows and just two attributes. Now, question 2. Rewrite the following SQL statements as relational algebra expressions instead. And I'll just drop the transcript up here for convenience. Do a select line item, or line num, sorry, item from line item where receipt ID is 123, and then a select when ordered from receipt where customer ID greater than 1 and customer ID less than 5. And the answer obviously is also in the transcript here, so we can enlarge that a little bit and get project line num item from select receipt ID equal 123 from line item. And then likewise project when ordered from the result of select customer ID greater than 1 and customer ID less than 5 from receipt. So a final word, by the way, on the notation. It's tempting to think that relational algebra just rephrases SQL as an algebraic notation, but that's incorrect on two counts. First, relational algebra is broader than SQL and follows slightly different and often better rules. Relations, for instance, are sets and may not contain duplicate tuples, even though SQL tables might contain duplicate rows. Now, such duplicate rows are almost always uselessly redundant, so it's almost always bad design for a working database table to include duplicate rows, even if it is allowed. It's better to adhere to the theoretical model of a relation as a set. That's one small example of theory informing practice. And the second point, it is misguided to trivialize notation. And if you doubt that, here's a small division problem for you. That's Roman numerals, in case you're in any doubt. Now, would you like to do that division without translating into base 10? I'd much rather compute 256, which is what the first value there is, divided by 16. The remainder, by the way, is 0. Good luck representing that in Roman notation. The point, of course, here is that the right notation helps you reason about complex ideas. And when you get into optimizing 15-line select statements with nested queries inside of them, you'll appreciate the cleanness of relational algebraic notation without all those selects, froms, and wheres cluttering things. And then by way of a final example on how we can use RA to think about optimization, just a very brief one, we'll do more a little later. Here are two relational algebra expressions, and this is for lecture question 3. Are the two expressions that are shown here equivalent? Do they produce the same resultant relation? If you think about it, yeah, they really do produce the same result. If you first select the tuple with customer ID 1 and then project it to just the customer ID, that produces the same result as first projecting the entire relation to customer ID and then selecting only the tuple with customer ID equal to 1. But then a follow-up question here, number 4. assuming a reasonably large relation, a reasonably large receipt table, is one or the other of these two expressions easier to evaluate? In other words, which order would you want to do the two operations? If you think about it, selecting the one tuple first is better, since then you only need to project that one tuple instead of projecting them all and then throwing out all but one of them. So the first of the two expressions is more efficient. Now that's a very small example of the kind of reasoning a query optimizer goes through to figure out how to perform a select statement most efficiently. And the next topic after theory basics that we're in right now will extend relational algebra, introducing operators for different types of join and for grouping rows, renaming columns, and so forth. And then once we have the complete set of RA operations, we'll look at a number of query optimization strategies, basing them on relational algebra.